Hi students, in this final video for online lecture 20, we are now going to talk about stoichiometry using our thermochemical equations. So as you can see, we are going to go back to an old friend of ours, and instead of grams to moles to moles to grams, we're going to be able to use our thermochemical equation and our delta H just like any instance that we've had before. So for other chapters, you have seen where we have used grams or molarity or volume. This time, what we are going to do is now use our energy. So the major goal when doing a problem such as this is get to moles. So whether you have a molarity, a grams, use your amount to get to moles. Then we can treat our energy just like any item from our balanced chemical equation. Biggest thing is you always want to verify that your equation is balanced. So let's try a couple of examples. The thermite reaction involves aluminum and iron 3 oxide using the balanced chemical equation that you see. This reaction is highly exothermic, and liquid iron formed is used to weld metals. We want to calculate the heat released in kilojoules per gram of aluminum reacted with Fe2O3. So the question becomes, what do I need to do to set this up? So the first thing that we need to do, and as you'll notice here, we do not have a delta H. Plus, we don't have other reactions that we can compare to, so we are not able to use Hess's law. The first thing that we are going to need to do is our products minus reactants math in order for us to have a good thermochemical equation. So let's go ahead and do that. Remember that our delta H is equal to the sum of the delta H of our products minus the sum of the delta H of our reactants. So we are going to need to get those values. So the first thing that I'm going to want to do is do our products. So that is going to be the delta H of our Al2O3 and 2 times the delta H of our Fe liquid. If this were a solid, that would be 0. But in this case, because it is a liquid, that is why we are needing the heat of formation for our liquid iron located here at the bottom. So then what we can do is plug in those values. So if we do that, we will get a negative 1675.5 kilojoules, this value coming from our textbook, plus 2 times our delta H of our liquid iron, which was stated as 12.40 kilojoules, and we would be able to get that value. For our reactants, notice that I'm only going to have one reactant value that I need because solid aluminum is in its elemental state. So if I do this, I am able to get my reactant value as just the value of my iron oxide. So if I go and look at my textbook, that value is going to be negative 822.2 kilojoules. So if we go and do a little bit of math as we're going along, you can see that our products are going to have a value approximately fairly close to negative 1650 kilojoules. And then you are going to see my 822.2, which we're going to have to add because of it being negative. So finally, we are going to get a delta H of our reaction to be negative 828 kilojoules per mole. Now, for a normal question in a textbook or a quiz, you would have probably already been given this or had some other way of providing this. But now that we've gotten it, we need to go and calculate the energy for 1 gram of aluminum. So now this becomes really important on how we're going to do this. So if I have 1 gram of aluminum, I then need to go back to my old friend, grams to moles, and say that 1 mole of aluminum is a mass of 26.982 grams. But now we are going to put in our information from our determined delta H. For the balanced chemical equation that we just determined, we are going to be able to get negative 828 kilojoules, not just per 1 mole, it is going to be per 2 moles of aluminum, because that is what is in our balanced chemical equation, that 2 coming from out front here. So remember, we're treating energy just like any balanced chemical equation, coefficient, and substance. So if I do this, I can now put all of this into a calculator, and you will see that I am able to get negative 15.3 kilojoules of energy per gram of aluminum. So now this is showing you just how much energy we would get when we have our aluminum. Let's try one more example. This example comes from the fall of 2016 and is actually a fairly notorious question. Propane fuel used in gas barbecues burns according to the following chem equation, in which you see propane burning with oxygen forming carbon dioxide and water. If a pork roast must absorb 1.6 times 10 to the third kilojoules to fully cook, and if only 10% of the heat produced by the barbecue is actually absorbed by the roast, what mass of carbon dioxide is produced during the cookout? So this is going to be a multi-step problem trying to figure out just how much energy we used, how much energy was actually produced by the grill, and to produce that amount of energy, how much carbon dioxide was produced during that. So let's talk about the energy that was absorbed by the roast. We start at 1.6 times 10 to the third kilojoules of energy absorbed by our pork. Well, if we have 10% efficiency in our reaction, we know that a negative 10 kilojoules must be produced by our grill in order for every 1 kilojoule to go in to our roast. So this is where the 10% efficiency comes in. If that is the case, we know that our grill has produced a negative 1.6 times 10 to the fourth kilojoules. So this is how much energy the grill actually produced, and only 10% went in to our pork roast. So now we have to look and see how much carbon dioxide is produced to make that amount of energy. Well, if we go and look at our balanced chemical equation, we can see that we are going to get negative 2,044 kilojoules for every 3 moles of our carbon dioxide. So I can now state 3 moles of CO2 for every negative 2,044 kilojoules. And because I asked for it in grams, I have moles currently. I need to go from moles to grams. So now this will be 44.01 grams of CO2 for every 1 mole of CO2. So my kilojoules and kilojoules will cancel, my moles and moles. I am left with grams, and I will receive an answer of 1,030 grams of CO2. If I look at my answer choices on the left, you will see that that is going to be answer B. In this video, we went back to an old friend of stoichiometry, but this time we saw that using the thermochemical equation with the delta H, we are able to calculate energy needed to produce for a reaction, or how much energy we need to get from a reaction, or if we know the energy, just how much a reactant or product was needed to produce that amount of energy. This now finishes up all of our videos for Chapter 10 and Online Lecture 20. Have a great day.